Okay, so good morning, everyone. So today I will start to continue a little bit on Laplace, Laplace transformation, and then maybe at the last 30 minutes, 40 minutes, maybe we can have some review on the topics that we are going to have in our quiz this Thursday, right? We have quiz, right? Or right? Do we have it now or next week? I forgot. Next week, right? Okay. So I think we can focus on the transfer. Okay, if that's the case, then we can focus on the higher order. So Laplace transform. And then maybe for review, we can have this Thursday, okay? Review for practice. Okay. And then next week, I would like to announce next week, no class on the Tuesday. So we have, so maybe let me write here. So no class on December 5th, right? No class here. We might have make up class, but maybe it can be this week or maybe next week. Maybe next week. Saturday. I will announce whenever I have confirmation. Okay. But for sure, no class for this Tuesday class. Okay, and then quiz is on the 7th, right? 7th December. Okay, quiz. This will be higher order, right? Differential equation. So that's it for announcement. I will write the announcement also in the Moodle later after we finish the class. Okay. Okay, now we can continue. The last discussion is on the Laplace. Okay. So, I think a little bit review. Whenever you see this curvy L like this symbol, we call this Laplace transform, which means everything inside here will be transformed through Laplace, which means we are taking the integration from 0 to infinity, and this is part of the transformation. And this will be the function that we are going to transform. Okay, so t to the power of n, this is the one we transform. So let's just take this into our integration. So I think we are going to use integration by parts. So taking the t and taking the e, we differentiate, we integrate. And then this will be t minus 1, this will be this. And since this t to the power of n, it can be derived or integrate with many iterations because of n. So when we set up that n should be a positive constant. So when n is a positive constant, that means we are going to use this result of the integration by parts. So we are going to multiply this and that. So negative t with power of n e negative st over s. This is 0. and what usually I'm writing for b. Okay, b, and then maybe write the limit in the front. And then plus n over s integration, or maybe limit, and then integration from 0 to b t minus n minus 1, and then e negative st dt. Maybe let me write a little bit down here so there will be much space. So if we look the structure, so this will be the same structure as we did in the previous one when we deal with t. Okay? And now we have this. Okay? So let me go zoom out a little bit to see what we have. Okay, let me copy this down here, okay, to get what's the conclusion. Okay, let me copy. And then let me write here. Maybe this will be going there. So this will be Laplace. Laplace of t to the power n. And this will be Laplace of t, right? Okay, or we can write the s can be factored out. I forgot to simplify. We can write this with s squared here. So this actually, the whole thing here is Laplace of 1. Okay. Do we have, I think this not, okay, this a little bit should be there. So 1 over s, okay, should be plus, right? So I think this is not really okay. So this will be Laplace of t is 1 over s multiplied with Laplace of 1. Okay, there. And so, by the same identifications, we see this one here is actually Laplace of t n minus 1. So we can simplify the whole formula for Laplace of t with power of n. the left part is 0, so this will be equal to n over s multiply with Laplace of t with power of n minus 1. And then suppose that we have Laplace of t n minus 1. Okay? Because we would like to know, like, if we have this here, what is this Laplace? Okay? So we can construct the same structure, and then construct another integration by parts, right? And then you will get that this will be equal n, and this will be s squared, okay? And then we have n minus 1 there, and then Laplace of t n minus 2, okay? On the right, here, we could try the real function, for example, t squared, t cubed. Okay? If we do that and do the integration by parts with the same structure, we get that if we have t squared, this will be 2 over s cubed, or this will be 1 over, or 1 over s, and then Laplace of t. That will be or 2 over s, sorry, and this will be 2 over s cubed, and so on and so forth. But for our general standards, we are going to focus on the t with power of n. So actually, what we have done here is basically, you see that this one is n, okay? And when n minus 1 will be multiplied n with n minus 1, and then n minus 2 will be having another multiplication and become like n cubed. And at the end of the day, actually, this, let me write this one over there. This L, or Laplace, t with power of n, this actually n factorial divided with s with power of n, and Laplace of 1. Or, since Laplace of 1 is 1 over s, okay, we can construct a new, more general rule for every power that we can write L, or Laplace. This will be n factorial divided by s n plus 1. So when you have t squared, this is supposed to be 2 factorial. 2 over 1, 2. So when you have, for example, t with power of 3 or 4, let's say 4, maybe let me write. This will be 4 factorial divided by s with power of 5. Okay. So this will be the general rule. Okay, now another simple transformation that that somehow we are going to see a lot is the trigonometric transformation. Okay, so the next thing. So again, let me just review on the early classes. So no class on Tuesday next week. We have quiz 7 December, and we might have a makeup class, but still not confirmed when. I will maybe within this week I will confirm when. Okay, so that's the announcement. Okay, so now let's try Laplace on. We have cosine and beta t. So the variable is t, beta is just a constant. So when you do Laplace, basically you do the integration and write the function on this side. Okay. And as usual, this is pretty much integration by parts. But I would like to set up the integrations by taking the e on the left and cosine on the right. So negative s e, negative st. This will be sine over beta plus, and then multiplications, and we set up the limit. This will be beta e sine beta. This is from 0 to b, and then plus. I will multiply and then factor out the s and beta because that is outside of the variable, right? And then write, so limit e negative st sine beta t dt. Okay. Okay, and then you could try to compute the limit here. Okay, you can come up with a rule, going down, moving downwards several times. 1 or 2. Will be 0. Okay, will be 0. You can try it like that, or just trust me. This will be 0. They try some L'Hopital, okay? Or maybe I think yeah, you can use some identity limit like sine x over x that will be equal 1 for limit x close to 0, but you can change x with 1 over t, and then you can you can exchange this with 1 over something that you can change the limit makes to from b to infinity. You can change b into another symbols 1 over b that is going to be 0, and then you will have some identity limit, and you can solve that, and practically this will be getting 0 on the left. Okay.
Sorry.
Yes.
For exam, are we gonna be asked to use for like the formula, or we can use the table?
Yeah, just use the table. Just use the table. Okay, just to get you to the introduction. Okay. So that's important. Okay. Do we need to prove this? Yeah. Okay. Okay, and then we have this one, which we need another integration by parts, right? So let's write again this one, and now it's sine, and this will be negative, and then derive the same, and then taking the positive and negative, and then we write and or maybe let me write this as this. Actually, the whole part of the integration is Laplace of sine, right? So we could set up Laplace of sine as, we can use the result on the integration by parts. So this will be negative 1 over beta. Oh. Okay, and then this will be limit. Oh, why? And then this will be, now it's so it's a positive, but it's multiplied again with negative, so negative s over beta, take limit, and then we see that we get the another cosine here, right? So when we take the cosine, we get sine on the result of the integration by parts. We take the Laplace of sine, we get cosine. So let me write here that Laplace of sine beta t, and this will be, because of this cosine, it will be equal to 1. So we have and then multiply with negative 1, it will be 1 over beta minus s over beta Laplace of cosine beta. So this is Laplace of cosine. So at the end of the day, these two Laplace, cos and sine, it will be related each other. So when we have cosine beta, this will be equal s over b Laplace of sine. And Laplace of sine is that 1 over beta minus something something. So s over beta. And write the Laplace of sine 1 over beta minus s over beta, and then Laplace of cosine beta t. Okay, and then we try to multiply. This will be s over beta squared minus s squared beta squared Laplace of cosine beta t. Okay, and then this is Laplace cosine beta t. Okay. And then we solve the equation. We move to the right side. So Laplace of cosine beta t multiply with s squared over beta squared oops plus s squared over beta squared Laplace cosine beta t equal s over beta squared so this will be s squared over beta squared plus 1 we can write like that. So Laplace of cosine beta t is we can cancel the beta squared, so s over s squared plus beta squared. Now because we have this cosine, let me write and make a space on the right side. So then if we have because we have the cosine and we also have the relation with the same reason, we can write this as s squared plus beta squared. This is s over beta. So we can cancel and cross multiply. So Laplace of sine become beta over s squared plus beta squared. So we get two transformation. So we get to transform a constant. We could transform the variable, and then maybe polynomial with power, and then we can transform the exponent, and we can transform this sine and cosine, the trigonometric basic functions. Okay, just a note, additional note that if we have Laplace, okay, and we have alpha, and then we have beta, and then another function g. Let's say alpha and beta are constant. So we could write this and separately writing the alpha multiplied with Laplace of f of t, and then plus beta multiplied with Laplace of g of t. Okay. So basically, we can set up, or we could see that this is actually the same reason with the integral. So you could think the Laplace, since it's actually transformation by integration, so all the property in integral that we have learned before is also applied within these Laplace transformations. So we are getting or expecting that this will be this. And another one is another integral. Okay, so this is what we call the linear property. So Laplace transformation is a linear property. Okay, just a quick note here, maybe on the next page. Okay, let me write on the next page. The sufficient condition, this will be, let me write here first. Okay. This is some transformation of some basic functions. I think the hyperbolic, the f and g, we are not going to use a lot. So I think we can just stick on the first 5, a, b, c, d, e, okay, at least for the basic transformation on Laplace. Actually, the next part after we define and getting introduction on Laplace, we have another one which we call the inverse of Laplace. So we are going to turn back the s into t. So why we need that? Because actually, to solve the equation, we simplify and we change everything into this s, okay? And then we can set up like some algebra within the s. After we calculate, we get the final result in s. And then to get the the final answer, or the one that we need to solve, we get back to the t. And then we need to take the inverse on this s. Okay, we call that in Laplace inverse transformation. But that will be the next section. So what I would like to say here is, let me just give you some example. And what does that mean? Okay. So if I have Laplace of 3e 5t minus let's say 3 sine 2t. Okay. So based on the table, we get that this will be 3 and then s minus 5, and then the other one will be negative 3 over, or this will be s, right? S is what? Sine is just beta over s squared, s squared plus 4, right? So 2 to sine to t should be 2 over s squared plus 4, right? So should be 6, right? Is it? Yeah, I think 6. Okay, since this is s minus 5 here, and this is related to this e, this Laplace, let me write Laplace e, it will exist on interval defined by s greater than 5. Because in order to have limit, or maybe let me write with another color, limit t closer to infinity, e negative s minus 5, right? T equals 0. We need s minus 5 greater than 0, or and same with the sign here, that we need to have s is greater than 0. Okay. So there are we call the sufficient conditions for the Laplace existence. The first point is integral in Laplace does not have to be converged. Example, Laplace 1 over t and Laplace e with power of t squared, like that. So the existence of Laplace depends on the Laplace f of t depends on piecewise continuous function of f on 0 to infinity. Okay. Why we need to take this interval? Because this is the definition of the Laplace itself. The Laplace can be defined from 0 to infinity. Okay. And f be of exponential order for any t that greater than some capital T that we can define. So we can set up the continuity in terms of piecewise. For example, this graph here is, we can decide like for several interval, we can have like piecewise defined functions with, it's actually like different function with different intervals. We can set up functions like that. So let me write here, f is piecewise continuous on 0 to infinity in any interval defined by 0 and at some point, so we can have like many t in between a b. Okay? So there are a finite number of points, so we can set up many variation of t, k, and k can 1, 2, 3 ... until n. At which the functions has finite discontinuity and continue on each open interval. So what does it mean is actually, this is, if you remember the improper integral, we can have like, if you think how we can integrate some functions, right? The functions need to be continuous, blah blah blah, and then it's integral, blah blah blah. But somehow in terms of improper integral, when we decide that we take the integration x, we take the limit, like it's getting larger, and suppose the, for example, we could have like 1 over x and 1 over x squared. We could define that the 1 over x becomes not going to be having an area, or it's getting divergent, and this one will be divergent. This is actually getting approached by that definition. Right here. So you can think like in the improper integral, whenever some integration become improper, either the limit endpoints getting infinity, or in terms of it has like some discontinuity, somehow we can take approach, and then we can take the limit and we can find the result, right? So this is actually just to get the idea that our function within the realm of the Laplace transformation, our function, as long as it is a piecewise continuous, and not only continuous, but it can be also a piecewise, and then we can define the interval in each point of t, and we can define, like for example, capital t1, t2, t3, like this one. We can define this piecewise continuous, and we can then transform within each interval, actually, using the improper integral. Actually, that is the summary. So whenever we use the improper integral, we could take the discontinuity here, and then we could somehow getting approach using limit, and we get actually approximately finding the result. Okay, similarly with our Laplace. So our Laplace, because it stands by the improper integral, so every part on the improper integral property will be applied within this context. Okay, we can take a break for a while. Okay, anyway, I think yesterday I put something in the model for your exercise, the higher order differential equation problems. So you could try to check that out for some exercise, and maybe this Thursday we can have a review, or maybe I can give you maybe another recording video on some solutions, okay? But maybe not all, because that's too many questions, but maybe some of the representative questions. So another point here that I would like to emphasize is that whenever we say exponential of order, okay, we need to define what is this exponential order. Okay. So we say that the function f is exponential order if there exists constant c, which we define also that another constant m positive and t also positive, such that the f of t in absolute value is less equal of m e with power of ct for all t that is greater than the capital T. And then right here, and then if the function is increasing function, then the f of t less equal m And this is simply states that a graph of f on t to infinity does not grow faster than graph of exponential order. For example, just with a random graph, for example, we have here the red one is the m e with our ct. And this is our comparison function, and we have our function that needs to be, let's say, to be transformed. So this f of t, the blue one, since it is not going to be faster than the red one, it means that this f is in terms with exponential order. So we say that the function f, this blue curve, is of exponential order because it is not faster than the red curve. And we can, like for example, depends on what function we have. We can design our exponent here with different constant. And we can say e to the power of t, e to the power of 2t. Okay. Depends on what is the comparison. So depends on the function that we want to see, whether it is exponential of order or not. So if we see from the left here, if we take zoom here, this is some example. Some example that says that, okay, let's start from the very simple, just a linear function. Since the red curve is going faster and faster than the blue one, we say, okay, this is also exponential of order. This is also the same. It's getting lower, and then it's getting faster. Okay, this is also the same. Okay, let me maybe write here that within this is. Let's say this is y equal t, so t is less equal e with power of t, and this is e, this is less equal e t, and here is 2 cosine t. Okay. And there are some unique case for the improper integral. Let me write here. Let me write over there. Okay. So if we have t with power of n, and this is m e c t, we can write this as t to the power of n over e with power of ct This is for, if we take limit, we could see that this will be final. But if f of t is e power t squared, and we can compare these two, or we can write like that. So as the e, this is also getting infinity. Or if we take the in improper integral, if we take the definition of Laplace, and if you solve this, you will see that this will be it will be divergence. So it will be that doesn't exist. Okay, as we see from this limit here, this is doesn't exist. Limit doesn't exist. So if we take the graph visually to see why this happened, this is because the e with power. Okay. So the e with power of t squared is getting faster than the e with power of ct. Okay. So actually, the exponential of order, when we see it and we can compare with the like the function, if we compare with the exponent, like e with power of something that is quite a standard e, and whenever it is the function is still less faster than the exponential order, we can say that the function itself is still within the range of exponential of order. That means that we can do the Laplace transformation. So if this happens, it means that this is not exist, or it's not exponential order. So e with power of t squared is not exponential of order. So that means there are two summary, okay, from all the long paragraph and words. There are only two summary that we can discuss. That first, the function is piecewise continuous. That's the first condition. The second one is the function needs to be exponential of order. So if both requirements satisfy, then it means that the Laplace for that function will be exist, okay? Whenever the s is greater than c. Like example, like before we see that s need to be greater than 0 or s need to be greater than 5, 4, 6. Depends on what is the function. And there are some proof here just to get you to get to know the formal definition. Then we can have a Laplace, and we can set up like 0 to t, okay, the capital T, which means that we treat as a constant that in between 0 to infinity, and then we have another t with power of infinity. We have two results. right? Two results. And then it continues to this. So this one exists as a sum of the integrations. And then we have the second integrations, and basically this is, we are using the comparison theorem in integration, if you remember, but I don't think so. Right? But this is actually just saying that like a squeeze theorem, like a squeeze theorem in the calculus one. So basically we can use the squeeze theorem in integration. We call that the comparison theorem. So basically we can compare that this one is actually will be equal to this one. Okay? So all this will be equal. So we get this result here. Okay? After we take some improper integrations, and then since it is converged, then the integration for this in the middle will be also converged, because this converged, this will be converged by the comparison test. Okay? And then after that, we can see that okay, it implies that this exists for some s greater c. This is coming from here. It needs to be s minus c needs to be greater than 0, which means that if not, then it will not exist, because if it's less, then it will be doesn't exist, right? It doesn't. Okay, so the existence for these two calculation I1 and I2 will be an implication that the Laplace will be exist. I think you can remember why we need to have this is because of this. So if the function is in a piecewise structure, then we still can do something about the Laplace. Okay, now as an illustration, let's see if we take the evaluation for some function that defined by this piecewise, it would be equal to 0 for 0 to 3, and then equal to 2 for t is greater or equal to 3. Okay, so if we draw the functions, this is just a constant, and then change the constant, and then jumping to another constant. So it seems that we have a discontinuity here, but we still can do something about the Laplace if we want to make the Laplace for the f, because as we define the Laplace to be exist, it can be exist if we have piecewise, and then if we have the exponential of order. So if both conditions happen, then it will be okay. And it is just a constant, so it's of course it is within the range of the exponential of order for the exponent. Okay. So basically, the way we do it is practically the same as what we did before. We can start by taking the Laplace. And since we have some jumping conditions or jump discontinuity, we can use that point at x at now is at t equal 3 to separate our integral. So we are going to have 0 to 3, and we can change the functions based on the piecewise. So 0 to 3 interval is 0, so this will be 0, and plus 3 to infinity of this 2, right? And then this dt. And of course, since it's 0, then we can ignore the first one and we focus on the second one, which this is basically taken up from 2 over s and then e with negative 3s, right? Or if we want to write maybe step by step, this is negative st 3 to infinity and s need to be greater than 0 to make it exist. Okay. Now the next is the next is the inverse transform. Okay. So basically the first part of Laplace finished and we get the inverse transform. Maybe later I will show you some exercise, but maybe give you this inverse first. So what is inverse? So let me write here the if left right capital F in variable s. It's representing Laplace transform of function of t, and we can write that Laplace of f of t is equal fs. Okay, now we can say that f of t is the inverse Laplace transform of f, the capital Fs. So we can write also the f of t is Laplace with inverse and then Fs. And based on what we've done, like for example, if we have a constant, let's say 1, this is basically Laplace inverse of 1 over s. And then t will be Laplace inverse of 1 over s squared. And then another one maybe e. This will be Laplace inverse of 1 over s plus 3. Now some inverse transform that we can deal with that in terms of this table. There is some basic inverse transform, and as I mentioned, the last two here maybe not so much we are going to discuss a lot. Maybe only the first 5, a constant, t to the power of n, exponent, and sine and cosine. So this is basically how we are going to reverse the transformation that we did in the first Laplace transform definition that we've done. So for example, if we are, let me write the example here. So if we take the Laplace transform or inverse from 1 over s to the power of 5. Okay, so we know that this is coming from the at least t with power of 4, right? So if we remember Laplace of t with power of 4, we have n factorial, right? So 4 factorial divided with s with power of 5. Okay, so this will be 4, 3 is 12, so 24, right? 24 over s with power of 5. We don't have 24 on this side here, so we need to multiply to make it equal. Okay, so this will be equal 1 over 4 factorial, and then this will be 4 factorial s to the power of 5, or basically 1 over 24 of t with power of 4. Okay. And then if we have Laplace inverse of 1 over s squared plus 7. So if we see from the definition on sine and cosine, if k is constant, and we see that this is a constant one, so the most possible way is sine, right? But we have k, so we need to multiply something with something, right? So we need to multiply with something. So if we have sine, let me write beta t. We take Laplace. This will be beta. This will be s squared plus beta squared, right? So if we have a 7, it means that we have sine square root of 7t. So this will be square root of 7 s squared plus 7, which means we need to multiply with 1 over square root of 7. So this basically 1 Laplace inverse of square root of 7 and this will be 1 over square root of 7 sine square root of 7t. Okay, okay, this is some basic example for the inverse. Okay. Well, in the real case, somehow, like if you remember that we can write the Laplace transform in terms of like many function in one take, it means that we can combine the s at the end, and by doing that, it means we need to separate the fractions. Okay, we need to separate the fraction. For example, let me get it into another example here. If we take Laplace inverse of negative 2s plus 6 over s squared plus 4. So we need some requirements to separate this fraction, and then maybe we can set up several fractions. Then we set up the inverse one by one. Okay, and sometimes it can be like a really like a complicated fractions, and you need some partial fractions to separate all of that. So yeah, it needs some time to solve. So this case, first we can take this into two separate equations. And basically we can write, and we can factor out the constant. This will be S over, and this will be plus 6 Laplace inverse of 1 over S squared plus 4. But I think since it's S squared plus 4 and the above equation is a constant, I will make this into just 2, and this will be 3, right? I think it's doable. And we can see that this will be negative 2 cosine 2t, right? And plus 3. This will be sine, right? Sine 2t. Okay. I think still doable, not really complicated. However, the case can be much more complicated, which requires the partial fractions. Okay. For example, I think you can write this first. I will wait for a couple of minutes. Okay. Now the next example is if we have Laplace transform or inverse. This will be S minus 1. So to solve this, the first thing is to separate. So we have a big fraction here. So first, we need to separate this fraction based on this denominator. We are given this 3 denominator. Well, if we haven't yet this, maybe it's still in the polynomial. So you need to somehow find how to factor out the polynomial. But it's already given here, so we can just write the partial fractions. So let me write here, so let S squared plus 6S plus 9. Okay, and then we can set up a partial fractions. And then we need to find all the components. So S squared plus 6x plus 9. A multiply with S minus 2, S plus 4, plus B, and then plus C. Okay. Okay, there are several ways to solve this. You can compute, and then one by one you grouping each together. But what I would like to show you, you can do this also. You can make S equal with some number, and then you can change all S with that number, and we find some equations. For example, for this case, I will use s equal 2. Here this will be 0, and 2 minus 1 is 1, 6, 1, 0, so it's another 0. So we have this equation. So we can let that s equal 2, or equal 1, or equal, yeah. So first, let s equal 2. So when s equal 2, so this will be 2 squared plus 6, 2 plus 9 plus this will be 0 plus b is 1 and 6, so it will be 6b. And then this was also 0. So this will be 4, 12, 16, so 25. So 25 is 6b. So b is 25 over 6. And then we can let s equal 1. So this will be 0. So 1 plus 6 plus 9 is 16. So 16 equal. So s minus 2 is becoming minus 1, minus 1, 5, minus 5a, right? So a is negative 16 over 5. And then let s equal negative 4. Negative 4 is 16 plus 24. 16 is 25. It's 1, right? 25 minus 24 is 1. Equal. Negative 4, 0, 0. This will be negative 5. And negative 6. So 30. So 30c. So c is 1 over 30. So we can substitute back the a, b, c to the equations. So we write in Laplace inverse. So we write, and then we can factor out the constant. So a is negative 16 over 5, and then Laplace inverse of 1 over s minus 1 plus 25 over 6 Laplace inverse of 1 over s minus 2, and then plus 1 over 30 Laplace inverse of 1 over s plus 4. This will be negative 16 over 5. 1 over s minus 1 is e, right? E power of t. Plus 25 over 6 e with power of 2t plus 1 over 30 is e. Now it's s plus, it's s minus minus 4, so it's e with power of negative 4t. Okay, so we get the result of the Laplace inverse. Okay, so it might happen, like you need to do some partial fractions, and it's like it's a part of the whole process. So sometimes maybe the partial fractions take some time to write, but still the principle is this Laplace inverse. Okay, the next is we are going to see the transform of derivative. So we are going to see if we have the derivative like f prime, what will be the transform of Laplace? Okay, so let me write in the new page here. So this should be the Laplace or transform transform was derivatives. Let's start with the Laplace of f prime t. This will be by definition 0 to infinity of e okay, and basically we start by taking the by parts integration by parts of the f prime. So taking the e and taking the f prime t, and the integrate will be ft. This will be negative st. Okay. So first is e negative st f of t from 0 to, let me just write infinity here. Okay, you know that this will be going to be the limit, but let me just write this to make it simple. I actually too lazy to write the limit, but let me just write this. Okay, and then plus s, and then integration 0 to, let me just write infinity, negative st ft dt. Okay, so somehow at this part we get negative f of 0 plus s, and this is a Laplace of f of t, right? This part here. So if we define that the Laplace of f of t, as we mentioned previously in the inverse, this is equal to capital Fs. So let's change to this, okay, to make it more sophisticated and simple. So Laplace of f prime t is basically s f of s minus f of 0. Let me take a line. Okay. And then taking another f double prime to see, can we make some patterns throughout the whole derivative system, like the first derivative, the second derivative, and then the third derivative, how will be the transformations, which this is going to be like a little bit closer to how to solve the differential equation at the end, right? So let's take another Laplace of the f double prime. So taking the transformation and take the integration by parts similar to what we have in the first derivative. This will be e and then f prime t from 0 to infinity plus s, and then this is pretty much the same, but the difference is now we have f prime t dt, and this is equal to the Laplace. So this whole thing here is Laplace of f prime t, which we can use the previous result to write the Laplace. So this will be equal negative f prime 0. The same thing with what we have in the first derivative, and then plus. Now if we have s, and then we are going to multiply with the Laplace of the f prime, which is s, f of s, and then minus f0. At the end, we have Laplace of the f double prime t. This equal, let me write the s squared first of fs, and then minus s f0 minus f prime 0. And you will see that when we increase our order, like third derivative, fourth derivative, we're going to see that this, for example, 3, okay, the third derivative, we are expecting this is going to be s cubed fs minus s squared f0 minus s f prime 0, and then minus f double prime 0. And if you increase the order, you will see the similar pattern. Okay, so we can write some general rule. If f prime f n minus 1 So basically, using this transformation on the derivative. So suppose that we have differential equation, we can Laplace transform, and then we can solve the algebraically solve, and then we solve for fs. So we get the fs, and then after we get the fs, we're going to be using the Laplace inverse, and we get the ft, or the solution. Or if you want to write with y, it's also the same, y of t. This is ys, okay, the capital Y. Okay, I think I will just end up till here. End up till here, and since I forgot to prepare the attendance, so no attendance here for today. I'm sorry. I thought I already prepared, but I think I am using this different link, so okay, we can skip that one.